So why navigation? Well, it's a real fundamental and a critical part of AI, interactive behaviour, and it's also quite difficult. If you've ever played a game before and found a character running on the spot, or a car driving into a wall, or a group of tanks or vehicles stuck in some spot, and you've gone, what's going on with this game? You realise that it's a bit difficult and it's important. It's not just a black box by itself. Issues relate to physics, steering, the way you design your levels and worlds. It really does touch a lot of areas of your game. And as games are become better, there's always an increase in the detail, the complexity of the world, the size of the world, and how do we deal with that with navigation? I consider simple AI, we're not talking self-aware, anything theoretical, just simple AI, to look a little bit like this, being navigation-centric. So imagine we have a character in a game, an NPC who's a guard, and he's in a behavioural state to guard a place, and then all of a sudden he hears a sound. So maybe an event occurs, some kind of sense occurs, he hears a sound, and so a reasonable thing to do might be to go, well, if the sound was over there, in the medium distance, I'll plot a path, maybe 50 metres, some point over there, and try and get to it. And so some path planning will occur, find a path some distance away, and the character will start to steer, start to actually take steps or movements, drive along that path towards their destination. As they go, as this guard we're imagining now, takes some steps, he bumps into janitor Bob. Bob's in his path. What's he going to do? He's going to switch back to path planning. He's going to take some steps around him rather than just face plan him. Continuing along, all of a sudden, bang, there's a gunshot. So, maybe the player's interacted with this NPC. We're going to need to make a decision again. Maybe he's going to switch to a duck and cover mode. He's going to plot a new path, maybe away from the gunshot or behind a nearby wall, something like that. So you can see how we're going from decision, path planning, steering, and sort of cycling back and forth in that. With those sort of tools, you can make some basic interactive game behaviour there. Dates about 2005 when I was trying to make a general purpose navigation system. These are the sources that I found most useful. An awesome article by Patrick Smith, who did the Command & Conquer Renegade AI. He did a presentation and has a Game of Future article there, definitely worth reading. Polygon Soup for the Programmer Soul. The Counter-Strike navigation bots, certainly good quality AI happening there. Use a navigation mesh system that's worth looking at. Path Engine, a third-party middleware that is doing the kinds of things that I was trying to achieve myself. The Unreal Engine, worth looking at. For me, Quake and Doom AI bots. Also, some of the modding community made some excellent AI for those. So that was my inspiration. I'm sure a lot of the current engines, Unity and New Unreal, have some great tools that you can just use. But if you're trying to write a system yourself or want to learn more about how it works, you look at the documentation for these. Slightly amusing story. After reading Patrick Smith's article, I was implementing something a bit similar, and I wrote an email to him about 2005 using the address on that website, and didn't get a reply straight away, and that was all right. About 2006, a year later, he did actually reply, and told me, sorry, his old email address he doesn't check that anymore. Unfortunately, that email ended up in my spam box. It was 2007 when I finally read his email. And wrote back saying, the question's a little bit obsolete. I've actually finished the project I was working on at the time, but good to meet you and so forth. Anyway, I guess in a couple of years I might hear a response from him. So as a programmer, the first thing you usually do when making a new task is make yourself a test bed and a test world. I figure that I need to navigate around a world. It should have some low objects to step over, some stairs, some bridges, some tall objects, things like that, objects that intersect. And so I made, since I can't draw to save myself, stretched boxes into all the shapes to make a world. If you can't tell what that is, that's it with a bit of shading. You can see some of those things intersect each other on purpose. Artists, God bless them, who can actually draw, they tend not to make precise things. If you ask an artist how tall is that building or tree, they usually won't say 2.3 metres, they'll say twice as tall as the character or about so big. Everything's a bit relative, and quite reasonably artists will put things together in a messy way from a programmer's perspective, and that's fine, because as tool writers we need to write tools that handle as much as possible and allow artists to create great things and not think about how many polygons they've used or whether some surfaces are intersecting or there's a T-junction there or something like that. They shouldn't have to think about that. That's our problem. So if you remember my CSG talk from a long time ago, I thought, great, I've got a polygon world. I can add and subtract polygons together. I can make a navigation mesh by just grabbing all my world's polygons and blending them in together into a single mesh. That was a really bad idea. It was incredibly slow, but not only that speed's usually a solvable problem. I found that the biggest problem was the question, is that a gap or a feature? So if you have just a gap in the world, literally something to step over from the game or jump over, a genuine gap between two surfaces, should that be there, or is that just some junk, some polygons that just didn't quite meet up? Now programmers immediately think of margins or epsilons. If that's a gap, we'll just calibrate the epsilon, make it a bit bigger, a bit smaller, so we can determine, or you just chase your tail with that. It really doesn't help. Is it a gap or a feature? Who knows? So a better logic was, what if we could take a step? What if we actually pretended to be a character in the world? We could take a step in every direction, and we could see, could I take a step there, or did I fall off a cliff? And make something, create some knowledge from that. And that's a really good idea. There's Marty in a box. Actually, sorry, I have to apologise. All these pictures are just snapshots that I take from whatever I'm working on at the time. Usually if something starts to work or if something fails miserably, I take a screenshot. Okay, so instead of taking a step in every direction physically or literally, what if we try to flood fill the world with steps? What if we pretend our unit is actually a box, a bounding box? What size box? Maybe as big as the smallest unit in your game, maybe a quarter of the size of your average unit or smallest unit. That's a good idea. What if we just flood fill the world with boxes, see where they land, see if we can connect those points together, and then try and make a 2.5 dimensional surface out of that. Okay, 2.5D, it's not completely 3D, but since we think of the concept of gravity most of the time, that's adequate. We need something that's, we want a tool that's fast enough to build pretty quickly and uses low memory. At the time I was working on a 2 gigahertz computer with 500 megabytes of RAM, one thread. So as a tool programmer, you need something where a level designer, a programmer, someone who's going to test the game regularly can in a few seconds start the game, or periodically, or occasionally use a few minutes. Anything more than that, and you're going to cause so much pain and frustration that no one will want to work on the game. They will not want to work on what they're supposed to work on, and they will certainly not want to try anything new. Okay, so that turnaround time between making a change in a level and actually running the game and seeing that change is really important. Also, whatever system we devise has to handle gaming features, doors, teleporters, jumps, ladders, those sorts of things, and moving objects. So here's what we're trying to achieve. If we can drop boxes from the ceiling or the sky, let them land on the ground. I just realised that my colours are totally whack. I've made a blue ground with green arrows, so it's not Jesus walking on the water. That's actually Gunman on the ground there. So I didn't realise that. Just try to make high contrast. That's the effect we're trying to get. Drop boxes, connect them together, try and find the world.
So the width of the box is the step size?
Kind of. So saying about the size of your smallest unit, maybe a quarter of the size of an average unit is a good metric.
Can this work if you're in a building or if you walk below a ladder or something?
Absolutely.
How do you handle bridges?
Yeah, good questions. We'll get to that. See if I can answer in here. So remember, trying to create a 2.5 dimensional thing, which means we do handle overpasses, multi-story buildings, bridges, that sort of thing. And the test level I was showing you there specifically has a bridge, at least one bridge there anyway. So this is actually the functions. I tried to abstract this. They look a bit like C functions without semicolons and types. If we can query a world and ask it a few questions, we might be able to get this information from it. In this case, we can test a box, just saying, box, is there anything inside you? Sweep a box, once again, it's a box, move it, typically from up to down or along the gravity vector. When do we hit something? Straight away, or is there some displacement there? Is a point in solid? That's good for testing, am I actually inside a wall? If you've got a box in level, are you in a room or are you actually inside a solid block of concrete? So am I in solid is a good question to ask. Polygon people will know often you can look at your polygon and if you've got a normal facing the wrong way, you're probably inside something. Test reach, that's really the stepping logic. It's can I take a step from an AI or logical perspective or a physical perspective, or is there something else there like a button, an elevator, a door that can allow me to access there? And the world bounding box. So you notice that those functions don't actually care about what the world's made of. It doesn't matter if it's voxels or polygons or anything. If you can ask those questions, you can build this abstract structure and navigate any world, or at least any static world at this point. So if we're going to drop boxes from the sky or from the ceiling, we have to find the sky and we have to find the ceiling. So we need to find all the empty space in the world so we can drop boxes. This is the algorithm I used, and when I was reviewing it I thought it might have been interesting, but in hindsight there's nothing interesting about it really. But I'll walk you through the process. If we grab the world box, so we're looking at a world side-on, we've put Gunman in there again so we can see that it's a side-on sort of world. We need to find the empty space, grab the world box, stick it in a list, pick a sample point, doesn't really matter any point, top left's minimum point, top left's fine, and try and grow a box. One grid unit in every direction, X, Y, Z, plus and minus, 6 directions. See if it grows, and in this case it's grown to there. So we then just subtract that rectangle from the world and we've got our first empty space box. We try picking the next sample point, oops, that's in solid. Our point in solid space has failed. We've got to cut the world up some more to find some empty space. Just cut it in half along the largest axis, divide and conquer. Still in solid space. Keep just doing this until we've cut space down till we can find a point. It doesn't have to be the same top left point, it can be any. Once we've found the space, that's all we're doing, just dividing the world, finding empty space. It really doesn't matter. And my algorithm I found was both lazy and greedy, which from a human perspective is bad, but in programming that's actually often efficient. That's what you think my final phase would be, but when I looked at my code it actually produced that. What it meant was my boxes happened to be growing bigger than the current cell that I was cutting it into, and that didn't matter because it just meant that it saved work for the next cycle. All there was boxes being subtracted from each other and also testing if they existed. I remember writing this system, took an hour or two and I never changed it because it was fast enough, and I'll show you some stats at the end of how long this sort of thing takes. So that's the result. We've dropped boxes, which I could skip back easily. We've dropped boxes from the ceiling like that, from the sky, and we end up with them covering the world, little red boxes all over the place. What can we do with them? Now that you've got sample points, you could actually navigate with that. But that's incredibly slow, and we've now got hundreds of thousands or millions of sample points. This was the logic. Literally every empty space box for X and Y, just the top two-dimensional thing, drop a box. Use the sweep box function. When it hits something, that's as far as it can go. That's the ground. So this was really slow and used up all the memory in the computer. So quite simply, I divide the level two-dimensionally into a smaller size and processed it. There was no dependence between any of those sections, so split it up into smaller portions, any portion that wasn't actually the level. This level is a box, but if your level is some enormous shape, which is empty space, keep cutting the world in half, throw out boxes that don't contain level. So these could be processed completely independently, but more importantly, we get to the next step. This isn't the next step. The next step is to actually get rid of the middle samples. So we only cared about the edges anyway. But if we join up those samples, if we call the connect function, can I take a step between the samples, you can see there on the ramps, at the bottom edge of the ramp, you could actually step up from the sides or from the front. But as you go higher up the ramp, it's now a bridge, you can't step. Instead, you can travel above it and you can travel under it. Both of those samples are connected together, but not top and bottom. Same with the little objects, you can step over those, but the tall ones you can't. You'd have to go around them. So that's what connectivity looks like. And you can see now it's looking like someone's dropped a cheese grater or something on top of your world. They've just found the walkable surface of your world, and that looks pretty cool. That's what we're after.
How did you drop boxes on the area underneath the bridge?
We found all the empty space. So the empty space included, yeah. The ceilings.
So you're basically dropping sample points down from the ceiling of any open space.
Exactly. Any empty box, drop it from the ceiling. And if you do have them stacked on top and they weren't merged, doesn't matter if you find the same spot. I just chuck sample points into an arbitrary. You have, as a tool program, you have a bunch of structures, whether it's standard stuff or write your own, just something you can query, quickly find neighbours or quickly test a point. Connect samples, each of 4 directions, can I reach, call that reach function on them, that's all. Pardon me, merging the samples. Naively, all you're doing with the samples is looking at the neighbouring samples and once again try to grow a full row, a full column. Sorry, destroying my clicker here. Try to grow a full row or column in any direction. And that's it, that's all there is to it. But what I found is that growing a full row or column in any direction looks pretty ugly. It may actually create we'll quickly script it here. That's what it looked like on first go. Long, skinny boxes. You can see particularly up in the corner, lots of really skinny, long boxes. Doesn't look very nice. Maybe creates a few more boxes. How can we alleviate that? One extra step. Just have a minimum size. That was just chosen by the user. You start off by saying, instead of having a minimum size being 1, let's say 8 or 16 or some larger value. And that's a seed, so it won't, as you pick a sample and try and grow it, which is nothing more than a few loops and growing in any direction. If you have a minimum size, if that seed only grew to say 2 or 3, toss it out, use another seed, pick another sample, grow out from there. And if you can't, can you imagine you get to the edge of the world, there is nothing left, you have to be small, that's fine. If you can't be less than the minimum, just use it. That makes sense to anyone. That produced, we'll just compare, we went from that to that. You see, long skinny boxes become sort of nice, roughly optimal shaped boxes just by using a minimum threshold. So here we're turning a large number of samples, those sample points, we're just removing all the interior sample points. The result is that. So remember though, we cut the world into small chunks to process independently. That's just to save memory. And now we cut out all the interior points, release all that memory, and we can merge them back together, just keeping their edge points. So now we can fit fairly large levels in memory and work on them for the final phases. The final phases is just grabbing our sector, and whenever 2 sectors bump up against each other, we look at the intersecting edge and we call it a portal. It's just the join between 2 sectors, and that's all we need. In general with navigation, all you need to navigate is a point or an area and a connection to another point or area. Okay, so you can imagine in the classic sense you've got a grid, a 2-dimensional grid. Every grid cell is a point or area. Its neighbour is a connection. That's all you need. So in this case we've got these large rectangular cells. We've got these portals or connectors. That's all we need to navigate. So that's just showing the same thing again. The purple edges are now portals that we've got. Okay, how do we get these other entities in there, these bridges, ladders, doors, teleporters, things like that? We just add more portals. So inside of a cell, we just mark in a level editor or something. These are manually placed. We mark a little region and we give it a portal. And that portal has a mechanism, and all it is an extra bit of metadata, a bit of data which says something like there is a door here, or there is an elevator, or there's a teleporter here, and where its destination is, which is just another portal in another sector. So all those things are supported just by adding portals with a bit of metadata. Or even this edge here is a spot. If the player or something, sorry, if an NPC, players don't need AI like this typically, if an NPC stands in this spot, they can then jump, and where they will land is this portal on the other side of the ravine or other side of some large gap. These are sort of data structures we're working with. It's pretty basic. Our sector has a bounding box and an array of portals, list of them. A portal is just a line segment edge and up to 2 sectors where it links to. And to support all of our fancy features, we have some mechanism metadata and the destination portal. So if you look at the data structure we've got now, we've basically got a navigation mesh, which is dropped on top of the world. It looks a bit like that. If I get rid of the original data, because we don't actually care about the world geometry, we've just got these floating little polygons. They're all axis-aligned rectangles, purely for simplicity. It's easy working with rectangles. Also, in my code, I worked with integers for the grid. Sure, you've got a floating point world, 3 dimensions, but just snap everything to your grid. Let your grid size be integers, and that way you don't have to worry about precision as much and errors and things like that. It actually works out very nicely. You just think of everything as a grid step. Everything's just these grid steps. Looking at my code last night, I didn't actually use these planes for much, but you would in some games. If you had a steep slope, which meant a vehicle would drive slowly up it or it would actually be impassable, you would flag, perhaps, you'd store some data in that cell so that when you do a path find, your weighting would choose to maybe go around a hill or around a steep slope rather than up it. Okay, so you store what data you need for your search algorithm, but we're not really talking about pathing algorithm specifically here today, because you can look up A star in Wikipedia or anything else, but I will mention it anyway. So if you can see there at all, I can barely see it from here. There's actually very, very faint lines. We actually have a starting point up in the top corner, which says start, a yellow line that goes to the end, and you can see that that's a path travelling through the system going via portals, cell to cell, via the portals. You really can't see it, I'm sure, but there's actually a fine network of lines, and those are the A star algorithm sampling, saying, what's the shortest path to this portal, to this portal, this portal. You can see it's scattered its search across a bunch of portals and cells toward the end. Unfortunately, I couldn't find this working testbed because this is a bit more fun. This was actually a prototype game to try and build Syndicate and Fallout type games. It actually used features of those like see-through walls and things. And that was a man walking around a couple of worlds, but I could not find that running. But basically what we're looking here is some of the pathing. So what happens when we meet a dynamic object? So far we've had static worlds, and we're just pre-computing a path once. We say from A to B, how do I get there? We can use a navigation mesh plus something like an A star to navigate it, to path find through it. What happens when something blocks your path? Well, just take a detour. In this case, we want a little path that's calculated very quickly. All it does is search a little bit around the current position of the entity and tries to get back onto the main path. So can you actually see what's on this screen here? You in the back? Probably not. This is a snapshot of it actually working, or me debugging a phase of it anyway. We have unit B, he's right there, and he's trying to travel along the green path. The green path actually goes way off the screen. This white rectangle here is just the part of the global path, part of the full path that's near the player, near this unit, sorry. He can't go through here because this unit's blocking it. You can see this fellow's right on top of the green line, he's blocking his path. That's a big tall pillar there, and the red's a bit confusing. It's actually a hole in the world made by the pillar, the navigation mesh there. So he has to recompute his path. These grey boxes are actually sampling out. So at runtime, it just puts a box around this unit, creates a grid in place, and tries to sample it, and says that's an empty spot, empty spot, empty spot, empty spot, so on. It just expands out, and it's actually checking, effectively doing a little A star as it goes. Can I get there? Can I get there? And you can see it's avoided B. It's avoided this object, and it's gone around there, and it terminates as soon as it reaches the global path again. So it very quickly tries to just make a grid to avoid a dynamic object that's nearby and get back onto the global path. Now, all of this stuff's been on these axis-aligned navigation mesh cells, and you might think those might produce but ugly paths. And they're actually not bad. They're not bad for a few reasons. One is that imagine that your world happened to produce this, so there were some other obstructions around, and so as the sample points turned into cells and the cells grew, as we showed the optimal cells, they might look a bit like that. And the yellow path goes through the portals, create some of that. But if you're going from there to there, you don't want to walk around through the portals. You just want to go straight there. That actually turns out to be very easy behaviour, because when you're actually steering along this path, all you need to do is ask, what waypoint can I see? You don't actually follow the path you've created. You target the waypoint. So even if you're driving a vehicle which has physics to it, it might accelerate and decelerate. It might have a turning arc, steering arc, things like that. You can let all that behaviour still work. All you're doing is using the waypoints as like, I want to get over there. Okay? This even works well with swarming behaviour and forces. If you've got a crowd of units around you, you can still let them push against each other. You can still let them deflect off walls. All you're caring about is targeting points in your future. And if you see multiple points in future, you just quickly work along them and say, can I see that? Yep. Ignore it. Can I see that? Yep. You basically target the furthest point you can see. So in this case, we can just ignore all those points and go straight to the destination. It is simple logic. There's no reason not to. You can also post-process it if you're really keen. You can fit curves through this. You'll need to be careful fitting curves. The can I see function. How does that work? Maybe don't use the Z buffer for that one. You can post-process these curves. You can trim the points. You can plot curves through. If you're doing curves, the curves don't know anything about the world, so you may need to step along those and make sure you haven't intersected something else. Okay. Now, there's a lot of stuff to talk about here, and it's really what comes to mind, or what questions you guys have. Because I'm obviously trying to recollect this from implementing this a long time ago. When you actually do traverse a path like this, you've got an AI character walking along, you cheat, okay? So just because your character has a physics system around him doesn't mean that as he's walking along the path, he has to obey that. If your character suddenly has an attachment, it might be some whopping big gun that has some kind of physical collision volume, and he might get stuck trying to travel on his path, well, you turn your clipping off, you disable that. Make sure he can always travel along, or he can be pushed around, or there's a feedback mechanism if he does get stuck that he then repaths at that point. Imagine that your character's moving along and then he suddenly gets hit by a rocket. Well, you stop him navigating and then you throw him with your physics system, and wherever he lands, then you see, can I actually navigate from here again? Otherwise, you might have to kill him. Like in the old Quake games, if you ever got outside the world, you just died. But you can be creative as to how you hide these problems, really. Network latency. You can imagine if you've got some kind of client-server system, maybe the server code is controlling the NPCs, and your clients are sort of doing some extrapolation, some sort of dead reckoning. That's okay, but you can pass on extra hint information. You might want to pass across the next waypoint or two, just so that it can make a better prediction. What if you have many paths and you want to process them simultaneously? Well, you're going to have to spread that out over time. You're going to have to do a little bit of one path every frame until you've got the entire path made, or you're going to do it asynchronously. You're going to make a request, give me a path. Your code's going to want to know when that path is ready to use. It's often easy with scripting, because with scripting your script thread, so to speak, coroutine or whatever it is, can often just sit there apparently and continue on. Depends what system you're using to how easy that is, but scripting can really help with AI coding. What if you have 100 units in your latest RTS game, StarCraft or whatever, and you select them all and say move over there? You've probably seen this behaviour if you played those games. You can guess and pretend. You can actually start your units pushing against each other, but also making some dead reckoning straight movement toward their goal. They can just start heading off toward their goal. Meanwhile, over the next second or two, the path is actually being computed, and then when it's ready, they can try and head along to their goal. You'll often see a unit heading completely the wrong direction, and then he'll turn around and go back. And you go, what did it do that for? Well, it's actually this sort of cheating. The thing is that most of the time, your unit will at least instantly move toward its goal. And if you can get that most of the time, then you've got a happier player. So the only thing I'd like to note about A* is that when I was looking up, I had a piece of A* code that I was able to plug in and use, but when I surveyed the web to see what was there, I found a lot of blogs of people talking about their version and so on, and I found that almost every single bit of code posted had bugs in it. So just beware that that if you grab some code off the web, it may not work. And I also realised that a bunch of them weren't even A*. They were something that worked vaguely like it. And so what A* is, maybe this is talking other languages to people, but A* is a common pathfinding algorithm. It's very simple, and it just uses the concept of a node or a point and a link, and it processes it to get from A to B. What's special about A* compared to Dijkstra, however you pronounce that guy's name, who writes a very simple algorithm, in the 1960s or so, probably at Xerox PARC or wherever everything in the world was invented at that time, is that it uses a cost estimate function using the distance to the goal to help it move. So if you had the classic Dijkstra, it actually expands out. It just takes effectively like a step in every direction, expanding out from the start until it covers the entire map. Usually what happens is you terminate when you reach the goal. And you can, because the Dijkstra algorithm finds the shortest path to every point on the map. So when you reach your goal, you've naturally found the shortest path to it. But it's very hungry. You can see it expands out. My programmer art there can't even draw a circle. Expands out until it reaches the goal. Whereas the A* heads directly toward the goal because it's trying to estimate. That next step is closer to the goal. I'll process that one, and it keeps going closer and closer. Hits the barrier. Yeah, it'll expand around it a bit, but it's very directed, and that's why everyone uses it. It's simple to implement, and it's directed toward the goal. It's faster. That's all that is. Oh yeah, heuristic cost. So A*, the whole point of it is you need this distance estimate function. What happens if there's a teleporter behind you? Well, it doesn't actually account for that. So if you had elevators or teleporters in your levels, just beware that the shortest path may be behind you quite some distance rather than in front of you. But in that case, if you did have things like elevators or teleporters, your game logic should say, where is my nearest teleporter? Can I get there? And then ask, should I take the staircase? These are some stats. I actually did find a game that this was used in and was able to build the tools. When you run 10-year-old code, it's always scary because you think it's not going to build and run. And it did actually build and run. It ran twice as fast as it used to. So obviously my computer now is about twice as fast as a Pentium 4 at 2 gigahertz. The box, this was a space game, and it had a lot of empty space. So this doesn't represent maybe the average game, but it's a game that actually did use it. 8 kilometre by 8 kilometre by 1 kilometre world. The grid dimensions was 10 metres, 10 metres for a grid. So that's loser 0 there. 800 by 800 by 100 cell positions. When the empty space search went through, it found about 900 empty space cells. It then dropped boxes from the ceilings and the skies and produced about 100,000 samples, which isn't actually that many in this case. Merged them together into about 5,000 cells and 10,000 portals. And the total process took, in my case, 50 seconds, but I do remember back in the day, this was one of the largest levels in the game. It took 2 minutes to run. So you can see finding space took 5 seconds, sampling the world took 5 seconds, testing reachability about 8 seconds, merging samples 4 seconds, and cell to portal connections 27 seconds. I don't know what it's doing there, but I have to look at the code. You can see the whole process was fast enough that if you change the level significantly, you got to wait a minute or two, and if you didn't change.
This would all happen offline as well. It wouldn't happen when you're loading the game. So.
No, that's right. This was a tool process. In development mode, you could trigger it to happen when you started the game. If you know you dirtied the level, there's a debug flag you could switch on, rebuild on the spot. Otherwise, it was done as this build process. Produced that cell portal file. Demo.
I imagine your system would go into threads really well as well.
Yes, certainly levels to levels and those little blocks were independent, so there was no reason not to. Let's see what we can do here if we Alt tab away from that. I haven't got 2 copies open, have I? I seem to have 2 copies open. Okay. I'm purposely running this in debug because I've got everything on and it makes it very slow, allows me to watch some stuff. This was a prototype game, and as is the story of most game developers, half the stuff you ever work on will be cancelled. So this is a prototype game that's actually very similar to Air Mech. Anyone played Air Mech? Anyone played Herzog Zwei? Neither did I. It turned out to be really similar. But it was actually inspired by Rescue Raiders, trying to make Rescue Raiders into a 3D game. What do we see here?
So this is a commercial game. Okay.
It got to, it's just another sad story. It would make me sad. Okay. Show what? Nav mesh. Okay. And show nav objects. Turn some stuff on. So actually we'll see if we can detach the camera. Just have a look. This is it's a test world and it's to test the gameplay, but you can see as a programmer you test stuff, and I'm testing the new scenery. There's a bit of a beach with some waves happening down there. But if we look to the side, if I can try and steer around a bit and... Oh man. How do I rotate my camera? I'd like to actually roll it back, and I'm not doing well here, sorry. I'm not doing well at all. Just trying to show you the navigation mesh, which is you can see there's like a high piece of ground over there. And you can see the world is still just turned into these boxes. So the whole world's been turned into boxes. I'm actually missing my numpad, which is probably why I can't steer around like I'd like. Maybe we'll just steer around this way. Better grab a unit while we're here. Tank. And another one. So we're actually trying to be a Black Hawk helicopter carrying vehicles around in a multiplayer game. Strange enough, the most similar game has Japanese style transformers picking up other things. So if we drop a unit there, we'll give it an order, go and attack the enemy base. You can see he's created a global path through the world, and off he goes. Oh yeah, I'm testing bloom and shadows and stuff, which is why the bloom is terrible. And you can actually see the shadow map being generated in the bottom corner there. We'll just block him off there. He's going to bump into him. You just saw then he created a local path around him. See the local path being made. We'll harass him again. Back onto the global path. Drop him again. There goes, flash of I purposely got in this mode so you can see the box flash up. If that happens fast enough, you can do it synchronously too, just because it's such a tiny operation. Yeah. Is there anything else you want to look at here? Probably not. No, so really just showed this static objects, dynamic objects, and the global path there. That is all, folks. We're up to, yeah. So.
Are we rebooting that game at all?
Oh, great. Not really, because when I. Questions. I got it to a playable point and played with co-workers and friends, and it was fun, and I realised it was fun, but I wouldn't want to play it all the time. I'd rather make a different game. So, no. But, yeah, so I learnt a lot from that game. Also, experimenting with interface, watching people play your game. Yeah, you learn an awful lot. So it was an interesting experience. And besides, AirMech is literally almost identical. So if that sounds interesting, go and download AirMech from Steam. If it's a free demo or play it, and it's the same kind of gameplay, looks beautiful. Interesting to see if that's successful, because my attempt was taking a 2D side-on game and turning it into above, and the decisions I made turned out to be almost the same as what two other companies' games made at different times. So as you work your logic going, how would this work? How would that work? And you end up coming to the same conclusion. But the conclusion is that, I want casual drop-in play and other things that basically aren't here. Yeah. So any questions, any thoughts on how stuff works? Or yeah.
I'm still not sure. If you can go back to one of the screenshots or your game or something.
Yeah.
Why you need the blue bounding box part? Like, why would you not try to trace, like, can I go as far as possible on that path and then see when there's like an obstacle in the middle and then reassess at that point?
Sorry, we're talking. Which part are we talking about?
Some like the later ones in the game, actually. Well, this was fine actually too. Yeah, let's say the blue boxes here.
Okay, so those blue boxes, I believe, are the portal edges of cells. So it's a.
Why would you need that?
Why would we need them?
Yeah.
They link the cells together. So the way I believe my code was doing it was each of these represents a box. The path that can be traversed is the blue line, and I used two-dimensional line segments to check connectivity. Can the width of this unit, remember we're making one data structure for all different size units. You might have a big army tank, or you might have a person or a mouse or something, a little rodent, and you want to know, can I fit through that portal? Also, can I cross? So as the pathfinder, as the literally A-star algorithms going between the edges, you'll be testing, can I cross this? Can I fit through it? And those questions will be answered to determine if there's a path there.
Okay. There must be different ways of doing navigation. How does this stack up in terms of best practices, this approach?
I'm not entirely sure, but I believe that this is common. The navigation mesh, so we're trying to take an arbitrary world, make an abstract data structure, as if we've shrink wrapped it or dropped something on top of it and let it find the walkable surface. This is common. And this method of flood filling, I believe in early Unreal, I think with the Unreal 1 engine, you can certainly correct me if I'm wrong, you had to manually place waypoints on the map and connect them together. That was how pathfinding worked. Then someone wrote a bot which actually walked a character around the world and sampled it and created that path automatically. Now this uses, as I said, the inspiration was the Counter-Strike bots. The Counter-Strike bots use a axis-aligned navigation mesh just like this. The third-party program Path Engine uses a navigation mesh that is not axis-aligned, it's just arbitrary polygons. Those guys are too smart for me, so I find that this logic is dirt simple. You know, working with two-dimensional boxes doesn't require any extra effort. Particularly if you deal with complex polygons, edges become a real problem where they overlap or intersect, and there's lots of errors. The Path Engine guys have a little article as to how they deal with it. They actually use integer math of a fixed precision to allow all ambiguities to be removed, and they do a great job with that. But that's a complexity. This stuff here is really simple. But I believe that, navigation mesh, however it's created, combined with something like an asynchronous A-star, and then some post-processing on the path to make it smoother, interacting with the systems as we described, that's turning it on and off, when to use it. And we didn't talk too much about steering, but steering is to me, building the mesh was an interesting challenge. This will work, this sort of logic works with many types of games, not all, many types of games. Typically a largely static world with few dynamic objects. If you've got a totally dynamic world, you might do something different. If you're making Minecraft and you want to move around, then your actual block cells form a natural grid. So you would probably just expand a search out along the grid. You wouldn't create a grid. You wouldn't create another abstract thing. Ironically, I used the only game this ever shipped with was a space game, which didn't have multiple levels and so forth. In fact, I only used the global path section. The local pathing wasn't used. As is true many games, look carefully. The ships and units can pass through each other. Turning collisions on in some of these games, it looks worse. So you look in an RTS game, often you have a big unit and his collision volume is very small. They can overlap and bump into each other. They tend to force each other apart. It's all smoke and mirrors. It's what feels good to the player rather than what is the proper way, perhaps. Any more questions? Otherwise, anything that comes to... Yep.
Something similar for pathing, like trying to predict what would be usual paths that units will have to take in the game and going like, you might as well take that thing instead of just calculating that every time you send it somewhere.
Absolutely, yeah. So this sort of stuff lends itself completely fine to a pre-computed path. If you've got a path that you've defined as a series of waypoints, manually configured. Remember we talked about those teleporters. You can create a portal. You could create some of this stuff yourself. You could guide it rather than having this, this dropping box tool. A section of a path which you simply connect to the endpoints. That's all fine. Those are all very good things. I believe the article that was most inspiring, that was Patrick Smith, I think his name was, he talks about that, using predefined paths, even copying the player. He said if the player can do something that you haven't realised, it's emergent gameplay, the player finds that he can do a running jump through a window, a rocket jump or something, get the AI to copy the player, copy exactly what the player did. It makes the AI look smart. So they're all really good ideas. And they do fit in, they complement, they don't conflict with this at all. Yeah. If you do have some more questions afterwards, just yell out and have a chat. And also, hang around for a few minutes, particularly if you're new, because there's a lot of guys here. We've got some veteran game programmers around and developers and so forth, and they'd be happy to chat with you, answer questions, get to know you, make some contact. Okay, thanks guys.
Thank you.